Good morning, I'm Davide Tonello and I work as project manager in STAM. I would like to present you the progress in the development of the STAM 1.2, namely the vulnerability assessment tool for industrial plants and infrastructure, which has been conducted within the activities of Work Package 7 during last month. Basically, the main goal of STAM InfraStress project is the development of a web application to carry out quantitative risk analysis and vulnerability assessment of sensitive industrial plants against physical attacks. In our mind, this tool should have three essential features. One, it should be user-friendly, namely the user should use the tool through easy actions, such as drag and drop, and the results should be shown in an easy dashboard. The second essential feature is that the tool should be powerful, namely it should make lots of computation in a while. And finally, the tool should be reliable, namely the results in terms of risk, impact, and vulnerability should be as realistic as possible. In this scheme, it is possible to see the software architecture of the vulnerability assessment tool. Basically, all the data concerning the tool are stored in a unique database created through MySQL. The backend, developed in Node, is in charge of retrieving data from the database, as well as store the data inserted by the user into it. Furthermore, it can set up and run the engine for performing risk analysis and then read the results. The front end of the tool is developed in Angular. The user interface serves for allowing the user to both insert initial input data and also view the results of the analysis. Finally, the access to the app, passing through the InfraStress platform, is managed through Fusion Out. In this way, InfraStress user can enter into STAM 1.2 using the same login. This is the standard workflow that should be made by the user when it wants to use our tool. Once logged into the InfraStress platform, it should enter into the vulnerability assessment tool through the common interface. Then, in order to have the necessary information to carry out the risk analysis, the user should interact with the graphic user interface to model its own infrastructure and define a set of possible conditions in which the infrastructure can be. Then the user can choose a configuration, run the risk analysis, and see the results in the final dashboard. Now, let's see the graphic user interface in more details. The home page mainly serves to manage the modeling of the user plant. In fact, the user can create the layout of its own infrastructure or edit it, define possible configurations, and run the risk analysis for each of them. It is worth to highlight the difference between baseline and configuration. The baseline is the layout of the plan as it is currently, while configurations can represent standard conditions, special events, possible modifications to the infrastructure. For example, unforeseen maintenance work to be carried out can represent a configuration to analyze, because it is foreseen that some information about the plant should change. The same can be applied if the infrastructure manager is going to change the layout of the plant, and, before this, it would run a risk analysis to understand possible improvements or vulnerabilities. This is a screenshot of the home page of the vulnerability assessment tool. As you can see, we have a box for the baseline and a set of boxes for each configuration. Baseline can be edited through the dedicated button, while configuration could be deleted, edited, or chosen to run the risk analysis. But the most important part of the graphic user interface is the mechanism which allows the user to model its own plant and the related configurations in order to give to the engine the right inputs for the risk analysis. The plant model is composed by the following elements. First, the area, which is the part of the infrastructure with special constraints. Second, the equipment, which is a machine or a device physically placed in one of the areas and useful for the standard functioning of the plant. 3. Security measure, which is a procedure or a device targeted at protecting the plant against attacks or incidents. The security measure can be plant-based when involve all the infrastructure, area-based when are effective only in one area, or equipment-based when protect only that specific equipment. In this screenshot, the first interface for modeling the plant is shown. In fact, the user can add areas to its own infrastructure by dragging them from the list in the left and dropping them in the box at the right. The same can be done with plant-based security measures, which appear as chips. In order to edit the area element, the user should click on Edit button and interact with the interface shown in the next slide. Here, each area can be configured in details. With the same mechanism of the previous interface, it is possible to add both equipment and security measures to the considered area. Furthermore, the user should also insert some essential information about area, namely 1. The average occupancy. It asks how many people are present. 2. The economic value of the infrastructure, expressed as euro for square meters. 3. The size of the area in square meters. And finally, 4. The presence of hazardous substances, according to the current hazmat classification. Also, for each equipment, it is necessary to add the security measures and the economic value to be used to compute the economic losses in case of an attack or an incident. Now let's see in details the engine which underlies the tool. The engine is mainly based on a powerful algorithm which has to compute the risk level and the vulnerability of each area of the plant. In order to do this, first the algorithm generates all the possible scenarios which can occur in the plant, combining the areas, the considered time slots, the considered threats, and the magnitude of a potential attack. As an example, if we consider a plant composed by 15 areas, 24 time slots in a day, 12 possible threats, and 3 levels of magnitude, the number of scenarios generated by our algorithm is 12,960, which is a very huge number. Starting from these scenarios, the algorithm simulates the evolution of each of them according to the presence of the different security measures. Indeed, the attack can be prevented, detected, diffused, mitigated, or not mitigated. Therefore, we basically have 4 possible outcomes for each scenario. Coming back to the previous example, overall, we have 12,960 scenarios and consequently 51,840 outcomes, which is again a very huge number. Once the algorithm has generated every possible outcome, it computes the likelihood and the impact for each of them. Then the risk is basically calculated with the classical formula, that is likelihood times impact, while the vulnerability assessment is carried out by giving an index of vulnerability according to some analysis considering only the impact. The results of the engine will be shown to the user through an intuitive dashboard containing charts and tools to filter the information of interest. The dashboard is still under construction and will be finalized in the next week.